Hi, I'm Nate Begeman. I work here at Apple with all these guys. And today I'll be talking about building a JIT in LLVM. And, all right, play. Okay. So I'm going to assume that none of you know anything about JITs or building one with LLVM. I'm going to cover some of the basics. Then I'm going to show a little example of a Clang-based JIT. So we're going to combine Clang, which Steve talked about earlier, sort of wrap that up into a library, use it to JIT some C code, and then we're going to figure out, sort of how many ways you can go wrong doing that, and, then try and do it the right way. So, in terms of doing it the wrong way, what we'll be focusing on today is mostly resource utilization on the system. So maybe you're using too many CPU cycles. Maybe you're using too much RAM. You're waiting for the disk too much. These are the things we're going to kind of cover. And to give us some notation for this, here's our little fake top view here, which your Unix tool, which shows you resource utilization. So here we see we've used 50 milliseconds of CPU time. So that's how much time the scheduler has actually let our process run and we consumed. Then we've got total time over here, which is CPU time plus time spent waiting for things like the network or the disk or whatever. And then finally, we get this fun macOS 10 column called rprivate, which is resident private memory. So that's not your code or anything else that could be shared with other processes. That's just memory that you've dirtied that's not going to be reclaimed until you call free on it or you exit your process or whatever. Doing performance work on macOS 10, this is one of the numbers we care about the most, since when you inflate the rprivate for your process, you're directly hurting all other processes on the system by forcing them to page out or whatever. All right, so what do you do with a JIT? Well, if you're building a JIT with LLVM, you probably first need to create some IR to JIT in the first place. So you can either take the approach that we're going to take today and use Clang, or maybe a PHP to LLVM IR converter, or something else, a piece of machine code that's going to generate IR for you. Or LLVM has a whole bunch of APIs for manually creating IR. So say that you want to create a wrapper function or a sort function by hand, you can do that too. And usually the IR you generate isn't going to be all the code you're ever going to run. You'll want to call malloc or printf or my crazy network calling function. So you need to know how to load some libraries. If you're loading libraries that contain IR, you're probably going to want to link them together, because then you can start taking advantage of LLVM's interprocedural optimizations. So if you have some code that calculates value or sorts values based on certain runtime constant values, but that weren't known at compile time, you can link those together, and LLVM's optimizers will throw away all the dead code when it's inlining and all sorts of other great stuff. And then you can do various optimizations and transformations to make your IR better before handing it off to the code generator, which Dan and Evan discussed in detail. So, loading libraries. There's two basic ways to do this with LLVM and the JIT. You can call this nice API that says parse bitcode file, and you hand it a memory buffer, which we created with a path, and I'll show you an example of that later. But basically it just says turn this blob of bytes into an in-memory representation of the IR so that I can go hack on it. And then, for code that's not IR, so you have a dynamic library of code that some other team at your company built, you call load library permanently, and basically it does a DL open on that, and it sits around in your address space. Then the JIT will go resolve symbols against that you call that it can't find in any of the IR modules. Totally simple. All right, so if you're generating IR by hand, you'll need somewhere to put it. In LLVM, we call that a module. It's just a container to dump IR in. And for the JIT, there are two basic important things about the module. First one is its data layout. So that's like what is the alignment of doubles and how big are they? And anything else I might need to correctly generate code for that when I hand it to the code generator. The other piece of this is the target triple. So my MacBook runs on an Intel processor. and someone else's FreeBSD system runs on an Intel processor, but they don't have the same target triple. It'll be, i686 Apple Darwin or i686 FBSD 8 or something like that. And you have ABI concerns. So especially when you're going to be calling external functions, the arguments need to appear in the correct order, and you need to obey the calling conventions for your target. So you should probably set the target triple on your module before handing it off to the JIT. If you used Clang to do this, it's probably set it for you based on the environment. But if you're doing it by hand, you'll need to set it. What goes in a module? Here's some stuff. So functions. If a function doesn't have a body in LLVM, it's a declaration. If it does have a body, it's a definition. So that's really easy. You might have some global variables. Again, they could have an initializer, at which point you own them, or they could just be a reference to some external global that'll be resolved by the JIT when you go and run your program. And then annotations, debug information. There's a whole class of other things that get jammed in modules that don't actually affect how the program runs, but you might want to poke at them for some reason. So now that we have all our code sitting around in memory, we need to link. Linking in LLVM isn't the same thing. It's not equivalent to running the linker, LD on your Unix platform. It isn't producing an object file or any sort of executable code. Basically what it's doing is concatenating modules together. The reason that you'd want to do this is because almost all of the passes, the code transformations, optimization, dead code elimination, etc., in LLVM work on either a function or a module. And if you're going to do cross function optimization, you have to be able to see all the functions. The passes don't know to check in with the JIT to go get a list of all the modules and do all that automatically. So we have a pretty, you link your modules together into one module, and then you go to town. The API for this is really simple, but a little tricky. So basically, you say you have a destination and a source module. You can treat it like a mem copy, except it destroys the source. So you say, here I have my destination module that contains some IR and my source module which contains other IR. You just call link modules, and you end up with one module. So basically all the stuff from source ends up in the destination, and source, according to the comments, isn't usable anymore, but it didn't delete it for you. So if you don't go delete it, you've just leaked a bunch of memory. So be sure to delete that. All right, and finally, optimizations and transformations. I can't predict all the JITs that you're going to go build with these awesome tools unless you steal my code. And in that case, you may want to run different passes. Some people may just want to, you may have optimized the code offline, and all you want to do is code gen it. Or you may be getting code from Clang, which does no optimization whatsoever. And so you're going to need to run the instruction combiner and other passes on that. The way we run passes in LLVM is with a pass manager, and it looks something like this. So here's some common passes that most JITs are probably going to want to run unless you've done a significant amount of optimization offline. You see we just declare a pass manager here on the stack. Basically what it does is it enforces an ordering and makes sure that if your pass needs dominance information or whatever, that goes and gets calculated before the pass is run. It's just sort of a bookkeeper for the various passes. You say, hey, here's my target. You pass it in the module so that it knows, when alias analysis is running and you're doing crazy pointer arithmetic on int pointers, that those are really 4 bytes apart, so it can take care of that. We've got an internalized pass here, which is a really great one. If you're coming from C or you were just creating it by hand, all your functions and globals and whatever probably got created with external linkage, which is the default. The optimizers have a little bit of a hard time with that because they don't know if somebody outside the IR that they're seeing is, hacking away on your stuff. So by passing an export list of this is what I'm really exporting, the optimizers can basically internalize all those external functions that you didn't care about and then delete them if they're not used, or inline them completely and get rid of them. Maybe figure out that some globals are read-only and propagate their value into all the code that read from them, stuff like that. We have a scalar replacement of aggregates pass here, which is pretty important if you're compiling an object-oriented language or you're using a lot of structs and arrays. it can break those things up so that the optimizers can get at the underlying elements of those objects without every optimization pass having to know how to dig into structs and know the target layout and all that stuff. Then we have an instruction combining pass, which is probably the most important one. And if you go and look at the various tools that run LLVM passes in the code base, you'll see people calling instruction combining 2, 3, 12 times. It is an extremely clever pass in that it knows how to convert, selects between -1 and a value into, an arithmetic rate shift and a modulo, and a leap year or something like that. But it's also really cheap, and it's a good way of cleaning up after other transformations that may leave cruft behind, or maybe the code you generated wasn't that great in the first place. And even though it takes, some non-zero amount of time to run, it usually results in getting rid of enough code that the subsequent passes run faster than it would have if you'd never run instruction combining in the first place. So if the code generator that Dan talked about knows all those tricks to get rid of DAG nodes, it would run even faster if the DAG nodes weren't there in the first place. So that's the instruction combining pass, and then you get to some IPO passes here. So we've linked these things together into our module. We've create a global optimizer pass. This is a great one for JITs in particular because it can say, I see that the internalize pass has made this function internal. It's way too big to inline it everywhere it's called, but I will change the calling convention from the standard C calling convention to my crazy fast calling convention where everything's passed in registers. It knows that it can do this because it's not external. No one outside your program can call this function. And because you're in a JIT, it's not going to live around for somebody else to call later. So basically, it can do transformations on your program specifically for a JIT that end up in noticeable performance improvements. And finally, function inlining. This is an inliner like you're all familiar with. It can, it will copy the bodies of small functions into the callers at the call site. Our inliner is relatively conservative, which is why you might, if there are functions that really need to be inlined, you might want to do it by hand. So there's also an inline function call. So you just pass it a call instruction, and you say, inline this, and it will do it, no matter how big it is or expensive or whether it was a good idea or not. So here's some sample code, for instance, that just finds every instance of every use of the function called inlineMe in a module, and replaces the call to inlineMe with the body of inlineMe. So pretty simple little loop. And that leaves us with code generation. So now that we have this most amazing pile of IR ever, how do we go run it and call it? Well, the JIT has two simple APIs for this. You go look up the function name in the module, gives you an LLVM function pointer back, and then you say, get pointer to this function. And what the JIT is going to do at that time is it's going to say, all right, operating system, I need some memory, and go make it executable. And I'm going to then run the code generator and dump the machine code in there. And all the LLVM targets not only know what the ASM strings for the instructions should be, they know the binary encodings. So it can then go assemble all the machine code and handle the relocations and all that stuff and jam it in this memory. And then it hands you a void pointer back, which you can then typecast to the appropriate function pointer in C. And when you're done with it, you just you call free machine code for function, and the memory goes away. So what does this look like? Were we to actually go build one of these things? Well, here's my simple little example. So I've gone and built Clang into a library, and I've made it export one function, which is C2module, which takes a C string, which is the source of my C program, and it hands me back an LLVM module back. And so here I call main. I've got get file, which is basically just a utility function that copies the contents of a file out into a C string. And I go into a loop so that we can see this happening over and over and over again. I call C to module on the source, and I get a module back. So now my module wants to call some other stuff. I want to go parse a bitcode file. So I've got my awesome extensions to libc called mylibc over here. You can see the memory buffer interface. It's just a path, which happens, so it's sitting next to my app. I go turn it into another module in memory calling parse bitcode file. So now I need to link these things together. You call link modules. It's just as easy as it looks. And we remember to delete the memory for the library since it's not valid anymore. We go get our pass manager. We register a bunch of passes. And you can see the last line here, this run. So at that point, the pass manager says, all right, I'm going to go do all this stuff. So we internalize based on the export list. We run the dead code eliminator. We run global optimizer and all that great stuff. So now we're ready to go run this code. We create a module provider, which is basically just a handle for the JIT to grab a module. We say, let's go create a JIT with this module, and give me the function, give me the pointer to my cosine, which doesn't actually compute a cosine, as you'll see in a minute. And then we say get pointer to function, and we print the result, calling it with the value 5. So what could possibly go wrong with this? So we have a JIT, and now we have a demo. So I will try and get this working. All right. So you can see, here's our demo source, which just jumped off onto another screen. All right. That's the function we're going to call. Not a cosine, as you can see. In fact, it squares a number. Just so you know I'm not fooling you or anything, here's the total source listing to this thing, which you basically just saw. So we're going to sit in a loop for 1,000 times, figuring out what the square of the first 1,000 integers is, which is the most exciting thing ever. All right. So we're going to run this program. And it can't find something. Oh, crud. This apparently needs to go onto my desktop for reasons no one understands. And it's totally not working. All right, so what you would be seeing, were this working, and it was totally working in my office, is you would be seeing a number print out every approximately 600 milliseconds, which isn't very exciting. So that's really slow. If someone asked you to go run your code, handed you that simple function and you took 600 milliseconds to JIT that, they would probably be very angry. So, and not only that, you used 31.5 megs of RAM to do it, which is way more RAM than like my first computer ever had. So, how can we make this better? Well, don't do anything we just told you. So, these were the things we did. Well, what can we do? We're going to optimize these areas. We're going to look at loading our library smarter. We're going to link modules in a more efficient way. And we're going to run our optimizations and transformations a little better. All right, in terms of loading libraries, what can we do? So there's a new function here that I'm showing you that says get bitcode module provider, which sounds a lot like parse bitcode file, except it hands you a module provider back instead of a module. So basically, all you're getting here is a handle. The only thing we've done is we've gone onto disk, we've looked at that bitcode file, we've read out the table of contents, but we haven't actually gone and turned any of the functions in that module into in-memory IR. So this is important because you probably don't want all 14,000 functions in libc instantiated. You're probably only going to use like 2. So, in partnership with get bitcode module provider here, there's a function called materialize function. Basically what that does is you call this on a module provider, with a function pointer that you got out of it using that same get function interface where you pass it a function name. And you say, hey, materialize this for me. And it goes out to disk, and it'll read the 82 bytes associated with that function. And it'll make it resident in memory. Why is this important? Well, most of the passes in LLVM don't know how to deal with things that aren't materialized, and they're not going to materialize them for you. So if you tried to inline this, it would say, oh, well, I don't see the body for that, so I'm just not going to inline it. And then you wouldn't get the performance you were looking for. So what if you don't need to inline things? So for instance, there's no reason, if you have a function that just computes a cosine of a value, to load the IR for that at compile time unless the function call overhead is so extraordinary that you really have to inline it. What you could do is compile that function to a shared library on your disk, and then use the shared library API to load that, and the JIT would resolve the function. So you really only need to load bitcode files for things that you really need to specialize, change, inline at runtime. For functions you just want to call, you probably want to compile them offline into a runtime library. So now we want to, what does it look like now that we've got this thing? Well, that's what we had up above. And now here, we still need to operate on that module, to get functions out of it, to link it. So you can see the module provider here has a method called getModule that just hands us back the underlying module that's in the module provider. So what does linking look like now? Well, it turns out that direction matters. So you can see here that our runtime library, when you load it, when you call parse bitcode file on it, it loads up to 20, it dirties about 20 megs of RAM. That's a bunch, because it has 14,000 files, or 14,000 functions. So since we only want those two, if we do it the other way, we can save all that memory. And the reason that is that link modules, as I said earlier, copies all the memory. It basically copies the entire contents into the destination module. So it is one of the only passes that will materialize on its own behalf in order to get this done. So now you've taken this library that's 20 megs, and you've got your generated code that's maybe 50K sitting around in RAM, and you've copied the 20 megs from container A into container B, which is now 20 megs plus 50K. So now you've got 40 megs sitting around in memory for no particular reason. If you'd linked the other way, you would have copied the 50 kilobytes from the library, from the code that you just generated, into the non-materialized module that was maybe 300K of table of contents and other stuff, and you end up with a 350K memory footprint for having all the code you care about in one module. So that's a 100x improvement. And not only that, you're not going to be spinning the disk reading a 3 meg bitcode file, which can take a while just on its own. So if you go look at the source code for this in LLVM, you'll see references to something called ghost linkage. This is a fake linkage type like external, internal, common linkage that we've made up to represent things that are in the module but haven't been materialized yet. So if you're playing with this and you get an assert that says, I don't know how to deal with ghost linkage, or I can't print functions with ghost linkage, what it means is that you didn't materialize something that you needed to first, or the pass has not been made aware of ghost linkage. So this is one of the areas where we are soliciting community help. If there's a pass that you really care about that you feel should run well with ghost linkage, like say the dead code elimination. So you just internalize the last external function you care about. You can run DCE. It should clean up after you. It doesn't, because it doesn't know what ghost linkage is. So what do we do with our transformations? Well, again, we can take advantage of the fact that we probably don't need to optimize the runtime library that we're loading, since we probably optimized it when it was built. So here we can run internalize, dead code elimination, and inst combine just on the code that we generated from Clang, and optimize that before we hand it off to the linker, so that we're just running our optimizations on a tiny little chunk of code, and we just assume that the runtime library was already linked. And the only things we have to run after link then are anything that would do IPO. So there would have been a demo here, but apparently my demos aren't working right now. So, and you would see it go like 20 times faster because it's just that much more awesome. And literally square numbers are flying past the screen. And so basically, that's because we don't have to sit there and spend billions of cycles calculating the IR and reading off disk for all these things that we're just going to end up throwing away after we internalize and run dead code elimination. So, and not only that, because we didn't have to load all that into memory, we only use 3.9 megs, which is still a lot of memory, but it's way less than 31 megs. That's right. Nobody does that. So, if you had a substantially smaller library, if you were JITting from a known little chunk of IR, you could potentially get that down to 1.9 megs or something like that. And we are always looking for ways to crank down on the in-memory footprint of our IR, reduce the code size and the memory footprint of our transformation passes. So anyway, you may have additional questions that for whatever reason might not be answered here today. Here are two mailing lists you're probably interested in. The main LLVM mailing list and the Clang mailing list. And web archives of these lists are available, so you can go back and see what, how we've shamed ourselves in the past. All right, who has questions?
What about more dynamic compilation? Actually, first a quick question.
All right.
Is there a generally agreed upon definition of JIT? Does that only mean like literally, you don't try to interpret it first?
Well, I mean, to me, a JIT means anything where you didn't have the binary laying around on disk to begin with, ready to go execute. So, in this sense, we're taking it to mean we just in time turned it into executable x87 instructions. It could mean you just in time interpreted your Perl from the command line, or I mean, I don't think that JIT is a really well-defined term, but basically it means I didn't ship you a binary that then you clicked on and the operating system just ran without any intervention.
Okay, so what about dynamic stuff like, what if that square thing, you want to say interpret it until you find out, whoa, that's a hotspot.
Sure. So LLVM has two different things. The execution engine has an interpreter. Unfortunately, it's somewhat limited since it doesn't get a lot of love. It can't handle vector instructions, for instance. There's probably other things it can't handle. But you can run you can interpret LLVM until such time as you're ready to turn it into native machine code. Another thing you could do is you could say, don't do any optimization, just call CodeGen. And it will turn it into moderately gross native instructions, and you can run that. And you can layer your own profiling on top of that. You could put intrinsics in the IR, similar to doing gprof at runtime or other profiling tools. And I mean, you're creating the IR. So you could, create atomically incremented globals for every function you're generating, and then go read them at some later point and say, oh, okay, I want to go dig that function out of the library. Run the optimizer on that, and then tell the JIT, throw away the machine code you've got for that function and recreate it. And then you'd spend your optimizing cycles on things that you actually knew were being running. For our test, for the demo today, clearly that didn't matter. It didn't even work. But whatever.
What about taking that a step further and saying, hey, I've noticed that square is called with 0 a lot. But sometimes it's not called with 0.
Right.
And I'll create two different versions.
Sure. So that's something, specialization, for instance. So that's actually really easy to do in the IR. Basically, what you say is create an empty function, call it X or whatever, or my square wrapper, and in my square wrapper say, if argument equals whatever, call this, else call square with 0, and then you say, hey inliner, go handle that for me, And it's going to actually just turn that into, if the argument doesn't equal 0, call square, else return 0. And hand you back the code for that. So I mean, you can create, by creating sort of generalized IR with whatever things that you want, and then saying, hey, go JIT this for me, you can sort of get whatever behavior you want. You can.
What if you don't know a priority that that's going to happen?
Well, I mean, if you had a way of recording what the function arguments were, you could create a switch table of the hot ones and, at runtime later.
Somehow you have to.
But the JIT isn't going to go do that on its own. So.
What would happen if the square function had called other functions that you hadn't?
Okay, so if they were in your address space, the JIT would just find them. So if you called printf, for instance, or whatever, it would just work. If you called, malloc or free. If you have another library that contains helper routines that you want to call, you have to register that with the JIT. If you have, that would be a precompiled shared library of other symbols. So, you could use the load library functions with that. If you had other IR modules sitting around that you didn't care about doing IPO with, you can just add them as additional module providers to the JIT. And when it says, I don't know where the symbol is, it'll go walk the list of module providers saying, do you have this, do you have this, do you have this? If you do care about optimizing across those boundaries, then you do what we did here. You say, I'm going to link these guys together, run my IPO, and then it'll find the symbols because they're all in the same module.
When do those functions actually get JITted?
They get JITted on demand. So basically, when you JIT a function and it calls external stuff, the JIT rewrites a call back into the JIT for that set call and says, hey, if I ever hit this, go do that. There is a global flag that you can set that says do not do lazy compilation, at which point it will recursively go JIT everything in existence, if that's what you care about. Okay. No, we don't. You could do that. We have a read cycle counter intrinsic in the x86 backend, for instance. So you could actually create, in the IR, you could create that instruction. Right now, you'd have to do it yourself. There's definitely a lot of opportunity for doing, runtime optimization, loop unrolling of hot loops, that kind of stuff. But we haven't focused on the JIT that much other than trying to give people a way to make it efficient and functional. Thank you.